Hey Yahoos, sorry I'm not here with you today. I'll be back on Thursday. You're pressing on without me. You're looking at metabolism and diet. We're also getting tests back from the energy unit, and you're going to do a little reading. But first, I'd like you to try this. We're going to do some calculations, and I would like them turned in just on a separate piece of paper, name on it by the end of class. I just want to see how your calculations are doing. We figured out that 1 calorie is 1,000 calories, right? And we also knew that 1 little calorie can take 1 gram of water and change it 1 degree Celsius, increase the temperature. So what I'd like you to figure out is this. From our previous warm-up, we said this pan au chocolat had 300 calories. This is big C. This is calories, right? So how many calories does it have? Figure that out. Yeah. The other thing is, if 1 calorie can increase the temperature of 1 gram of water 1 degree Celsius, how much can 1 calorie change the temperature of 370 grams of water? It's about like a soda can's worth of water. Yeah. Figure that out. Cha-ching. Use a little dimensional analysis from your math class. And then therefore, theoretically, how many degrees could if you took all the energy in the pan au chocolat, put it into a 370 gram can of soda, how much would the temperature change? Try to figure that out. Discuss the value you've calculated. Does it seem a lot? Does it seem a little? Is it expected? What do you think? Cool. Try that. It might be a little bit heavier calculations, but I think you can figure it out. Turn that in at the end of class. Cool? Oh, my driver's off. All right, moving on. That was home learning. Today, you're getting your tests back, and we're going to go over them quickly. I would like corrections done, and I'd like the test to be handed back. Cool? I'd like to see what you kind of gotten from this. So, really roughly, here's the gist of this. In this first part, they're talking about the activation energy, and the activation energy is going from here up to here. This is the activation energy that you need to put in. So I'm looking for this piece being labeled AE, activation energy. The delta H, the change, is this piece, right? This is delta H. This is overall change in enthalpy. It's not this. Nah. Right? It's not that. That's the change from the activated energy state to the lowest energy state. But so these are the two pieces we're looking for. Cool. How does this show that it's exothermic? Well, the initial height up here is higher than lower height, right? This piece, the energy is basically going from here down to here. So this is high energy, right, in the molecules. This is low energy, right? I'm just sort of making this without the bump in it. So it's going from high to low. It's like going a cup of hot water going from hot to cold. That heat, that energy has to come out and go to the surroundings. So this is exothermic because it starts high and then goes low. Great. Moving on, flip it over. Ping! We did some calculations. You guys did pretty well with those calculations. This ended up being like 3,009.6 joules, and you showed me this. You just dumped in the numbers, and you showed me your calcs here. This was 4,299.43. You took this number and you said, all right, we got 3,009.6 joules out by burning this much fuel, which is 0.7 grams if you subtract, right? So you're going to say this divided by 0.7 grams, and that gives you this piece. Cool? Great. Oh, if you messed up this one, if this was wrong, but you used the wrong, like if you had 12 for up here, but you used 12 down here, and did it appropriately, you probably see DTPE, means due to previous error. So you got knocked on this one. I said nope, or you got less points. But this one, you did the right thing with the wrong number, and so we don't want to dock you twice for that. So probably that's right, and it says DTPE, if that's the case. Cool. Flip it. So same sort of thing up here. Complete the balanced equation. This was 1 and 2 and 1 and 2. Oh, this was O2, right? Combustion means you're combining fuel with oxygen. You're getting CO2 out and H2O out. That combustion is always this out, right? The numbers may vary. This piece explained in terms of energy why the bond making and bond breaking, it gives you an exothermic reaction. There's less energy required to break the bonds of the reactants than is given off by making the bonds of the product. There's a net out. That's just short and sweet. Give me something to that effect. This, you did a bunch of calculations. You got negative 103 kilojoules per mole. You looked at breaking up all of these, breaking up all of these. The only hiccup was that you had to use different values for these. Let's see, we used yeah, great. All right, moving on. On the back, this says, all right, let's do the same sort of thing, but instead of using chlorines, let's use bromines. And they said, let's see, this is this many kilojoules per mole, which is less exothermic than previous, right? On the previous page, we got negative 104 or whatever it was, 103, right? And this one's only 45, negative 45 kilojoules per mole. So what might be the difference? Well, I'd like you to explain in that either there's less energy out and reasons for that, or more energy in and reasons for that, or both. We don't know that it's just one or the other, right, without doing more research. So it's either this or both. That gets you the 8, right? This guy on question 3, you had to be careful because this just says change in temperature, and it didn't say which way the change went. So if you didn't look at the data, if you just quickly ran through it, you got duped because we went from start temperature 19 down to 9, right? That's a decrease in temperature. All of these are negative, right? 20 to 16, right? These are all decreasing in temperature. So if they're decreasing in temperature, it's the solution's getting cold because the energy is being pulled out of the solution and into the energy of the bonds of the molecules. So this is endothermic. Yeah, careful reading and interpreting. Describe fully as you can the trends shown. Well, you'd say something like increased volume that you're using, or the increased mass that you're using, or increased amount yielded an increased temperature change, but only up to a point, right? It's important to note that, like, hey, look, as you use more and more mass, it increases until this point, and then it just tops out and kind of stays the same. So you'd say until until 8 grams are used, and then it stays at 10, blah blah blah, right? Describe what you see. All right, moving on. The leaf blower. Josephine's crazy uncle has got a leaf blower, and so this is going from chemical energy and turns it into kinetic because it's moving air, and also sound is given off. Some people put heat, but it said and as heat energy, so this one can't be heat. Great. This ends up being 48%. Make sure you can get that. This ends up being 8 joules. Be careful with your basic calculations. All right. On the back, what does the waste energy have on the surrounding air? Well, it heats it up, right? Waste energy is heat, so it heats the air up increases the temperature, whatever you want to say. This piece on C shows the outside temperatures of a CFL and an LED bulb after they're switched on. So here's the CFL. Oh, apparently can't hit anything. And here's the LED. It said one advantage aside from higher efficiency. So don't tell me it's higher efficiency. What other good things? Maybe one is that the LED, this one, doesn't get as hot, right? Doesn't get as hot. And that's good for the efficiency, but aside from the efficiency, it's safer, right? It's safer. If you put your hand on this 70-degree bulb, it might get hot. It might set some fabric on fire if it's on it. We're not sure, but this is a cooler bulb, so therefore safer. So that's one advantage. Ching, doesn't get as hot. Also, it reaches max brightness faster, right? So this sort of tops out. It starts being at its maximum brightness here, and the LED starts being at its maximum brightness here. So it reaches maximum brightness sooner, which means that you don't have to like wait for it to warm up. Ping, it just is on. Great. Moving on. Last page. Ooh, this was the good one. Alrighty. So with this, they gave you the chemical makeup of this, and when you calculated this, you had to look at energy in and energy out. You subtracted them, and you were looking at activation energy. So this is the amount of energy that the weight has to impart on the material to get it to release all of its energy. So we have to put this much energy in. So you subtract these two numbers, right? And when you do, you figure out how much energy the mass has to give off. Well, the mass can only give off energy because it has potential energy, right? So that's mass times gravity times height. We know the mass is 20K, so 20 kilograms times, I should probably put that in, 20 kilograms times 10 meters per second squared. And the height is what we don't know. But we do know the potential energy that it has to be this or greater. So we put that in there, and I think that's like 2,340. You solve for H. The only hiccup is that these are in kilojoules, not in joules, so the height ends up being something ridiculous like 11.7 kilometers instead of 11 meters, as you might think. And so that's the number you're looking for at the end for this one, and then describe in reality why it might be why it needs to be dropped, and it's all about efficiency, right? I think I may have written efficiency of transfer, EOT. Really, we don't know that the mass will impart all of its energy to this pile of chemical, and that the energy will go into the bonds. So we need to drop it from higher than this, which is kind of ridiculous, to make sure that all of the energy goes in, right? It's going to have to be higher than that. Neat. Cool. So that's that part. Actually, corrections, turn it in. I want to see it. If I've made any mistakes, highlight them big and write me a little blurb about what you want me to look at. Great. So we're looking today at, well, you're looking at metabolism and diet. We've got a little bit of a reading piece. We also want you to be able to get information from videos, but also be able to read things and analyze them. So in your fancy pants booklet on page 12, ping, is this weight loss and metabolism reading. Read through this, right, 12 and 13, and on 14 there's a handful of questions just to analyze your reading comprehension. This will be up on the VLE if you have lost it someplace, and that should be just fine. Cool. So these are the discussion questions, and that'll be all coming back in when I see you next. Cool. So sorry I can't be here with you, but soldier on without me, and